So let me share with you another test to find if you have a maximum or minimum value. So recall, we were looking at where we had max and mins by looking at where our function was increasing and decreasing. And we saw that if we found that our derivative was increasing to some value, x equals c, and then decreasing, and our function was defined at x equals c, then we had a max that occurred at x equals c, but the max value, remember, we had to plug that back in to our original function, and we found that that was max at f of c. We saw that if we had something decreasing and then increasing, maybe at some x value of b, and it was defined at our original function at f of b, then at x equals b, we have a minimum occurs. And that minimum value, we plug it back into the original, and that would be f of b. So this was looking at the first derivative to find local max and local mins. But there is the second derivative test, and this doesn't always work, but let me just go through it. So it says, first, suppose that at x equals c, we have a critical point of f of x. So recall, to have a critical point, that was that the derivative was equal to 0 at that value. Or it was actually undefined at that value too, and that's not put in here. And let's say that the double derivative of f of x is continuous in the region around x equals c. Then if we find that the double derivative evaluated at that critical point or critical value of x equals c is less than 0, it's less than 0, concave down, then it's a max value. If the double derivative evaluated at that critical value was greater than 0, we had a concave up, and so that's a relative minimum value. It's inconclusive if you plug in that value c, that critical value, into the double derivative and you get 0. Then x equals c can be either a relative maximum, relative minimum, or neither. So that test, our second derivative test, doesn't tell us anything about it, and we'd have to go back to that first derivative test. Personally, if I was going to have to graph this function, looking at where it's increasing and decreasing, it to me is a lot easier. And then I'd also have to find concavity. So to me, the first derivative test is a lot easier and it tells me more, and I prefer that, but the second derivative test also works. So let's look at an example. Okay, so our example says f of x is equal to x plus 3 raised to the 4th power. And then the direction says find any critical numbers for f, and then use the second derivative test to decide whether the critical number leads to a relative maximum or relative minima. If f double prime of c equals 0 or f double prime of c does not exist for a critical number c, then the second derivative test gives no information. In this case, use the first derivative test instead. So yeah, f of x equals x plus 3 raised to the 4th. So we first want to find our critical numbers. And so we need to find the first derivative. And I noticed that when we take the derivative of this, we're going to use our chain rule. So the derivative of our outer. So bringing our power down, we have 4 of the inner, which is x plus 3. Subtract 1 from our power, which is a cube, times the derivative of the inner, which is 1. Okay, so looking at this, I'm looking at when this is equal to 0 and where it's undefined. I notice that this is defined everywhere. So looking at when this is equal to 0, we have 4 all times x plus 3 quantity cubed equals 0. Well, if I divide both sides by 4, I get x plus 3 quantity cubed equals 0 divided by 4. That's just 0. If I take the cubed root of both sides to get rid of the cubed, the index is odd, so I don't need to put the plus or minus. I get cubed root of x plus 3 quantity cubed is just x plus 3 equals cubed root of 0 is 0. So solve for x, we'd subtract 3 on both sides. We get x is -3. So this is our critical number or value. It wanted us to use the second derivative test. And so we need to find the second derivative. So let me just write the first derivative right here. So we saw that the first derivative was equal to 4 times that quantity, x plus 3 quantity cubed. So taking the second derivative, I'm going to have to use the chain rule. So my outer function is this quantity cubed. So bringing down that power, multiplying it to that 4, that gives me 12 of the inner x plus 3 quantity cubed times the derivative of the inner. Well, derivative of x plus 3 is just 1. So if I look at this, my pen stopped not working anymore. Unfortunately, when I plug in that -3, wherever I see an x in my original, that's going to give me back 0. Not in my original, in my second derivative. So that -3 plus 3 in that quantity gives me 0. 0 cubed is 0 times 12 out front is 0. And so the second derivative test in this case is inconclusive. So that didn't tell me anything. I have to go back into the first derivative test. And so I have -3 here. I need to check on the left and the right, and I need to plug it into my first derivative to see where is it increasing and where is it decreasing. So if I go back in, I want to choose something to the left of -3. So maybe choose, how about x equals -4. So if we plug that into the first derivative, we have -4 plus 3. That's a negative number cubed times 4. So that's going to be a negative number. So we know that it's decreasing until we hit x equals -3. So let's see what's happening on the right of x equals -3. So if we choose a number bigger than -3, so how about 0, and we plug that into the first derivative, we want to see, is that positive or negative? Well, 0 plus 3 is positive. 3 cubed is positive times 4 is positive. So the first derivative evaluated at 0 gives us a positive number, which is greater than 0. And so this is increasing. So something that is decreasing to increasing, where it's defined in the original, which it is defined in our original, then I know that I have a minimum value. So a min occurs when x equals -4. But to find that minimum value, we have to go back in and plug that into our original. I'm sorry, not -4. I don't know why I said that. Probably because I saw the -4 there. It occurs when x is -3. So let's plug it back into our original to figure out what the y value is, and that's the minimum value. So we're looking at what is -3 plus 3, that quantity raised to the 4th power. Well, -3 plus 3 is 0. 0 raised to the 4th is 0. And so the minimum value we get back is 0. So another way to write that, it's at the point -3, 0. Okay, so today we looked at finding higher derivatives. So being able to find more than the first derivative. We looked mostly at the second derivative, but we could go higher by taking higher derivatives. So third derivative is derivative of the second. The 10th derivative would have been the derivative of the 9th derivative. So you'd have to take it 10 times. We looked at finding concavity, what it meant to be concave up, concave down, looking at the point where we changed inflection, where it changes from concavity, concave up to concave down, or vice versa, our inflection points. And then we looked at finding that using the, looked at that given a function by finding the second derivative test and looking at when that was equal to 0 and testing values. And then we looked at the second derivative test for max and mins. And we're going to stop there because we just have like 2 minutes left. And I'm noticing my computer, for some reason, the internet is a little off right now.